Hello guys, so welcome back to our course. This is lecture 9 and we're gonna continue our discussion about diode circuits and applications. So if we, review quickly the flow of our study for diodes, we started by the exponential model. We solve the circuit using this, complicated exponential model in which we have nonlinear equations. And I hope we can, master such kind of circuits right now, or by this moment of the course. And then we make some approximation, and we dealt with a new model called the constant voltage model, in which we, approximate this exponential relation, into an easy way or an easy model to solve quickly diode circuits in a pretty accurate way, by the way. And now it's turned to the third model and last model for the diode, which is called the ideal model, the diode ideal model. This model, although it will look for you at the beginning, as not accurate, but it's really very fast. And for some application, you can consider it accurate. And this application basically digital circuits. And when you have a very high input, very high voltage source, with voltages, much larger than the 0.7 of the transistor. The transistor when it conduct in forward, it has, approximately constant voltage, which is VD1, which we call VD1 in the constant voltage model, which is for silicon diodes usually 0.7 volt. Okay, good. So let's see now what is this ideal model now. So the ideal model is exactly the constant voltage model, except for some, one observation. So basically here, this is VBI, which is approximately 0.7 for silicon. But for others, it's 0.3. For germanium, for example. Another diode called Schottky is also around 0.3. So it's basically very small. Even the 0.7, it's also very small. But if the inputs or the kind of voltages in the circuit are really big, much bigger than 0.7, and there are many applications with such characteristic, in which you have voltages much larger than 0.7. Or if you remember in digital circuits, 0.7 was considered low because it's closer to 0 than 5. Digital circuits usually we have 5 volt and 0 volt, 5 volt and around is high, 0 volt and around, the voltage closer to 0 volt are considered low. So it doesn't matter if the voltage is 1 volt, half a volt, 0.7, 0, minus maybe minus 1. All such voltages are closer to 0 than 5. And for 5, the high voltage, it doesn't matter if you have 6, 5.5, 4.5, 4.3, like some like one of the examples that we took. So all these are considered, close to 5. So all of this can be considered high. Okay, the absolute value doesn't matter for such applications. Okay, so the approximation here is that we're gonna consider VBI 0. So we're gonna consider once the diode is in its forward bias, okay, it is just conduct. Once it's in forward bias, it just conduct, and the voltage will be 0, the voltage drop. So it doesn't need even the 0.7. This may be weird for you now, but as we go in circuits, we're gonna find this, pretty accurate. Like for example, the example that we're gonna, cover today. So let's, draw such or locate such approximation. So let's, have, for example, let's try red. So basically, as I said, once you are in forward, you will conduct, and the voltage drop across the diode will be 0. So basically, this will be approximated to that one. So for forward, once you see that the diode is connected in forward bias with the source in ideal model, okay, then it's on, and there will be a current greater than or equal to 0, and the voltage drop is 0. So this is the forward. Okay. Now, how about the reverse? The reverse is exactly the same as constant voltage model. In constant voltage model, we said that this current IS is very small, and if for even some there is some region in which the current is even lower than IS. So basically, this will be 0. And I'm gonna do it in another color so you can differentiate. So this is reverse. Okay. So in reverse, let's write these down here. Okay, these characteristics basically. So number 1, forward diode is always on. Once you see in forward, it's on. The voltage drop, VD, constant equal to 0. Once you see the diode forward, VD is 0. Number 3, ID greater than or equal to 0. You said it's on. Why it's greater than or equal to 0? Because basically this point, this transition point, is belonging to both. It's a transition point between off to on or on to off. Okay, that's why you may find the current equal to 0. That's fine. That's for forward. Okay, how about the reverse? So in reverse, diode is always off once you see it, just like the constant voltage model. So nothing new here. So exactly equal to constant voltage model. No new stuff here. Okay, diode is off. ID equal to 0 because it's off, basically. And VD must be negative. VD is less than 0 as an absolute value, -5, -4. Okay, so must be negative or equal less than or equal to 0, again because of the transition point here that belong to both regions, forward and reverse. Okay, but you can't find it positive if you assume the diode is off. If you have some doubt if it's forward or reverse, and that's may happen for you, that you have a circuit in which you can't determine directly if the diode is forward or reverse. Again, you can assume forward or reverse, prove or disprove. Okay, if you assumed it's reverse and you find the voltage is positive, then you have something wrong, and this assumption is not correct. And if the assumption is not correct, then it's forward. You don't have other options. Okay, so that's basically the constant voltage model. May you have breakdown? Yes, if we have a breakdown, then let's continue this with this colorful. This color is similar to what we have originally. So black, for example. So if you have a breakdown, then you just go breakdown like this. Let's continue the green. Let's go back to this. So this is minus VBD. So let's also summarize the breakdown here. So number 3, the breakdown. This is again just same as constant voltage model. Nothing new. In which VD constant equal to VBD. Of course, in minus, must be minus. And ID as an absolute value greater than or equal to 0. Why it's equal again? Because of this point. It's a transition again between reverse and off and the reverse and on. So basically, once you see a current, either positive or negative, okay, in that region, in either regions, forward or reverse, we can consider the diode is on, but on in reverse, in breakdown this time. And that's why we keep saying breakdown, not on. Just to differentiate, to have some differentiation between the characteristic of that region in reverse and the on regular region in forward. So this is our regular on is the one in forward. Basically, for most application, we want to avoid the breakdown. But if you have the model how to deal with the diode in that way. Okay, good. Let's see now an example in which we talked before, but we solved it using the constant voltage model with 0.7. Let's solve it now, okay, with the ideal model. This was an OR circuit. You remember, guys, the OR logic, okay? So let's see if we solve this using the ideal model. Does that change the conclusion that this circuit is an OR circuit? Okay, that's basically the catch, that you can use the ideal model, you will get a very fast solution for your circuit. At the same time, the conclusion will not change. So let's do that. First, let's start by VA equal to 0, VB equal to 5. And why I didn't start from 0, 0 like here? Because I'm gonna conclude something from this assumption here. Okay, as if you remember, guys, when we assumed VA or one of the inputs is 5, when the input either VA or VB is 5, the diode was on, and when the input was 0, the diode was off. So you can basically, if you started by this, you can know or have an idea in the following combinations like 5 0 or 0 0 or 5 5, which will be on and which will be off. Okay, so let's assume here that DA is off and DB is on. Why? Let's check. So basically here, the minimum voltage in the circuit is 0, the ground. There is no source here. The source basically is our inputs. So once you don't have a source, you don't have how can you have a current? Okay. So basically, when we put V is equal to 0, so basically here B is connected to 0, and N is also closer to a 0 voltage. So basically, how it can conduct. Okay. So we assume that, or we have some doubt that there will be a current in D1 under the ideal model for the diode, and or even the constant voltage model. Okay, but for VB it's 5, B is close to 5, N is close to 0, so you may have a current flowing in that way because the voltage on B is greater than the voltage of N. Okay, good. So let's see. When we assume DA is off, okay, then the current IA is 0. And when we assume DB is on, then VDB is equal to 0. Remember, this is the ideal model. Ideal model. Okay. So V out, the voltage here, V out, equal to, or let's do it in another way. So VDB is basically VB minus V out. So VDB equal to VB minus V out. And VDB is 0. And VB is 5. And V out is unknown. So from that, V out will be equal to 5. If you remember, guys, in that problem, when we solved it before using the constant voltage model, V out in that case was 4.3. Now it's 5. There is 0.7 difference, right? Okay. But this, the question is, does this will it change the final conclusion that this is a circuit of OR circuit? We're gonna see. Okay. So at VA is equal to 0 and VB is equal to 5, we get V out equal to 5. So where is this? Yeah, this is the one. So here it's a 5 volt. Okay. Now let's check if our assumption about DA is right or wrong. So VDA, okay, let's call this DA and DB here, is equal to VA minus V out. VA is 0, V out is 5. So it's a minus 5, it's reverse or off. So our assumption is correct. Okay. Good. Number 2, let's do this in another color. Let's do lighter one. Yes. VA equal to 5 this time, and VB equal to 0. It will be the opposite. You know, these are, you know, identical branches. You know, you just switch the voltages. So we'll just have the opposite case. I mean, here the DA will be on and DB will be off. DB is off, then IDB is 0 or IB is 0. DA is on, then VDA is 0, because again, this is the ideal model. Okay. So VDA, which is 0 equal to, let's check here, equal to VA minus V out, which is unknown here. V out is, or VA is 5, and V out is unknown. So 0 equal to 5 minus V out, so basically V out equal to 5. Again, if we look back at our solution with the constant voltage model, V out was 4.3. So again, there is 0.7 difference, which is big. It's around 20% or 15%, right? But again, the question is, does that change the conclusion? That's the basic question that we should answer by yes, or I'm sorry, by no. It doesn't change. That's why we can use the ideal model, and we're gonna see this. So with 0, 5, with 5, 0, we still have 5. Now let's do 0, 0. Again, another color. So let's take, you know, blue, for example. Number 3, VA 0, VB 0. We see that when VB, when any input is 0, the diode is off. So basically, we're gonna assume both are off now. So DA and DB are off. Okay, off means they are in reverse or at the transition point, like this one here. We're gonna see. We're gonna see. If they are off, then IDA equal to IDB equal to 0. Then let's assume the current here is I. Here is IA or IDA. Here is IDB. So basically I is equal to IDA plus IDB. 0 plus 0 is just equal to 0. Good. I is basically V out minus 0 over the resistance R. V out, so I is flowing in that direction. So this point minus this point, which is 0, divided by RL. So basically here, which, and this is of course 0. So V out will be equal to 0. Just, you know, multiply by RL, then add 0 to both sides. So V out will be 0. So in that case here, V out is 0. Finally, let's do the last with red, for example. VA equal to 5, VB equal to 5. So we notice that when any input is 5, the corresponding diode will be on. So here DA and DB are on. Okay. So VDA equal to 0. Again, this is a constant voltage model. Okay. So VDA is equal to VA minus V out. VA is 5, V out is unknown. So V out equal to 5. To check, we should get 5 again if we do the same using VDB. So check here, very small check. VDB is 0 also because again, DB is on. This is equal to VB minus V out. 5 minus V out. Again, you're gonna get the same voltage. Okay? So at 5, 5, we have an output of 5. Let's now look. Okay, let's draw, a kind of, axis or something. Here is the 5 volt, which is the high voltage. Here is a 0 volt, which is the low voltage. Okay, so basically, when we have 0, 0, we have 0 here. So it's basically low. When we have 0, 5 or 5, 0 or 5, 5, we have 5 volt. So it's basically high. Okay. So basically, when you have low, low, you have low. When you have low, high, you have high. When you have high, low, you have high. When you have high, high, you have high. That's OR gate. So, although V out was different, V out with such a same circuit when you solved it before using a constant voltage model was 0, 4.3, 4.3, 4.3. Okay, but still 4.3 or 5 or 5.5 or 4.9 or 4 point whatever, all such voltages are closer to high, which is 5 in that case, rather than 0. That's why they all consider the same thing, high. That's why the conclusion doesn't change. Okay, that's why we can use the ideal voltage model with with high confidence, we can say, in many applications, and still we get very good result, because again the conclusion doesn't change. Okay, and we're gonna see examples, more examples when we take or explore another applications for the diode, which is the rectifier, in which you usually have very high input voltages, and the output is equal to V input minus VD. And when VD is 0.7 and the input is, for example, 100 volt, so 100 minus 0.7 is 99.3. And if you consider VD it's very small. I mean, if you consider VD is 0, it will be 100. Just you neglect the 0.3 difference, 0.7 difference, which is the same basically. Okay, so that's a very good introduction for the ideal voltage model. Now we took all the models for the diode. Okay, now you are ready. You basically ready to solve any circuit, based on the givens, and I mean based on the requirement. Do we want this? Do we want to solve the circuit in a, the most perfect, accurate way? Then you go to the exponential model. But you have very high complications. Do you want to have an idea about which is on, which is off? Very fast idea, or does your application, is not that sensitive to VD? Then go with the ideal model. If you want to gather both, something fast at the same time, easy to solve, go with the constant voltage model. Okay, so that's basically why we study each of them. Okay, so see you in the next videos with more applications for the diode. Thank you very much for watching, and see you soon. Bye bye.